In this course, we're going to look at computational aspects of GFEM. So we will basically see today what are the things that you have to do in order to implement a generalized finite element code starting from a finite element, a displacement-based finite element package. So we will see that there are basically two different algorithms to do this depending on how your functions behave inside the element. So if the functions, the enrichment functions that you're providing to the elements, remember these clouds, we talk about the idea of patching or pasting together all these different clouds where each cloud has some behavior that we want to represent or reproduce. If the enrichment function in those clouds is smooth, so then we just need to perform the integration in a similar way to what we have done already in standard FEM. There are some differences in the way we are computing the enrichment function and the derivatives, because normally enrichment functions are a function of the global coordinate x, whereas our shake functions are a function of the master or master domain or the parent element. Now, there is another case where we are dealing with functions that are not C infinity, so these functions are not smooth, like for example the ones that we saw in the previous course, where the functions are discontinuous. And in these cases we actually have to split our main element in what we call integration elements or integration subdomains. So this is a case B we will discuss later today. There are these two different approaches to perform integration. Okay, so let's start by basically defining what are we going to be integrating. So if you remember a scalar field, let's just rewrite the GFEM approximation for a scalar field. We can write our approximation, and U in this case, for example, would be the temperature. It's a function of, let's say, a two-dimensional coordinate x. So this is the simplest way to represent that generalized finite element approximation, where if you remember, these were your generalized, in this case, scalar degrees of freedom, okay? And these are our generalized enrichment functions that are, as you remember, the product of the shake functions and our enrichment functions. And of course, this whole expression can be written as just the product between this vector that we call phi and the vector that describes the degrees of freedom for the entire system. So you're in a way your solution vector that contains not only the standard degrees of freedom but also your generalized or enriched degrees of freedom. Now for a vector field, the approach is similar. The only thing that is going to change is that now we're going to be using vectors. So now our UHP is a function of, it's a vector valid function . Now the degrees of freedom are also vector. But then nothing else changes. Everything remains the same. Okay. And if you look at that, those vector operations, you can for a 2D problem, then it's slightly different than for 1D, and you have phi 1 1, 0, 0 phi 1 1, phi 1 dl, phi 2 1, and of course this is going to continue, and since we have n nodes, then we're going to have phi n dl. dl, remember, is the size of the enrichment space that we're using, and this is going to be multiplying our degree of freedom vector, that for this case it was, let's say, this is x, y, un dl, x, un dl, y. It's going to look something like this. Yeah? Okay, so now that we have a means to represent our approximation, remember that we're dealing with a Galerkin approach, so the whole weak formulation led us to the discrete formulation, and everything ended up in abstract form as find u h belonging to some, well, in this case let's call it hp, belonging to some space or energy space that is valid on that omega h, which is our discretization, such that our bilinear form UHP BHP is equal to L BHP for all VHP belonging to that space, or energy space. And this basically is the abstract way to say, well, we're interested in this problem, and depending on the type of differential equation that you're solving, then the bilinear linear forms are going to take one or another form. Okay? So this, of course, led to our system of linear equations. So at the end of the day, we're interested in solving numerically our Ku equals F system. Yeah? And if you remember, K is our global stiffness matrix, was obtained by performing some sort of sum, an operation that we called assembly of local stiffness matrices. And then our force vector similarly is obtained by performing an assembly of local force vectors, F sub E. And if you remember, well, these local stiffness matrices were written as integrals over the respective finite elements, and then B transposed D B d omega. So B was a strain displacement matrix, D was our constitutive matrix, and then for the force vector it had the contribution of two parts, one due to body forces. So now here I'm already focusing on the elasticity problems. So d omega, and for the traction boundary conditions there was a term on gamma t where this was Let me see here. I cannot seem to find, yes, now it is here, okay. And this is our traction vector, and that is a boundary integral. Yeah, so now we're interested in obtaining these quantities within the generalized finite element framework, right? And what we saw in the previous class is that the only difficulty is once you compute the enrichment functions, you just have to add them at the back of this, let's say, generalized shape function container, right? But once you do that, the rest of the implementation is the same. So that is basically the only difference with respect to standard FEM, that we have to figure out a way to, from the shape functions of the partition of unity, that let's say we put them in a vector, we have to expand this vector to include the enrichment functions, right? But once we do that, then we can readily do computations like this. Those are involving the shape functions and the enrichment functions. This is not going to change. Everything else remains the same. Of course, I'm not talking about the number of Gauss points, which may increase depending on the enrichment functions that you use, right? Now, in terms of derivatives, there is also a little bit of a difference there, because this matrix, the strain displacement matrix, in standard FEM only contained the derivatives of the shape functions with respect to global coordinate x. Okay, now things are a bit different, because now we have enrichment functions, and you have basically the generalized enrichment functions, which are the product of the partition of unity shape functions and the enrichment function. So to obtain the derivative of those is a little bit more tricky. You have to apply chain rule. But once you have those, then you just also have to augment this B matrix to include the contribution of enrichments. But once you have done this, everything else remains the same. Everybody with me there? Yeah? So now the only trick is, okay, how do we compute these quantities? And then how do we put them in a container, in the same container, so that we can use the same underlying displacement-based finite element package in a generalized finite element framework. Okay? So we have to perform these integrals, and we can basically divide this task into two cases. So let me write that down. We have two cases. Case A, the integrand is a smooth function, or C infinity, on omega A, which is omega A is the element. B, well, the integrand is not C infinity. Yeah. So those are the two cases. So let's start with case A. So let's draw our parent. Say that's our parent triangle. These are my master coordinates, psi eta, and that is mapping to a triangle in physical space that looks something like this. And then I'm using integration points. Say I'm using 3 integration points. So these would be my integration points. And let's say those map in physical space. So there is this mapping we discussed many times before that basically takes you from the parent or master element to the element in physical coordinates. So here we're basically just performing integration with the aid of a master element, the same way we do integration with the standard finite element method. Yeah. Let me just move this. Yeah. And that master element, if you remember from the advanced finite element course, we call it omega hat, and this is my omega e. Okay. Now, the same things that we learned in our advanced finite element class apply here. So in our master element, we have defined our shape functions as a function of the psi eta coordinates. And for this particular case, well, alpha goes from 1 to 3 because we're dealing with a triangular element. And then to obtain the derivatives of those functions, we just apply the change rule the same way we did it in standard FEM before. And I can copy that, and I only need to change these ones to y. And if you remember, we're actually not doing that operation the way I'm writing it, because we found a nice way to do this with a matrix operation. So the derivative is basically using the Jacobian matrix, the inverse of the Jacobian matrix. That's the way we do it. Yeah. Okay. So that is the only difficulty, I would say. Once you do that, then there is a little trick, because we need to compute the enrichment functions and their derivatives. And because of the generalized enrichment function is the product between our shape functions and our enrichments, to obtain derivatives, we just have to apply the change rule multiple times. But that is the only trick here. So what I wanted to do is to give you some idea of the algorithm that you have to think when you implement this. Okay. So let's take the first. Let's take this. So let's say we're going to try to integrate that. So how would the algorithm look like for that? So we want to integrate this. We say we are using our isoparametric formulation, so the geometry that we're using remains linear, right? And so we are transforming that integral into an integral that happens at my master element. I'm going to just write it like that. Where I have the Jacobian, or the determinant of the Jacobian matrix, right? And then this is going to be D, and I'm going to do kind of the same, just to keep consistency, okay? But you see what it means. I'm basically performing the integral over my parent element. So let's write the algorithm to do this. And here I would like to have some of your input, okay? So let's discuss. Who remembers how we did integration for, let's say, a standard 3-node element? So we for the assembly, we do have a loop over elements, but for each element, and this is what I want to discuss first with you, what did we do?
We have a loop through each of the Gauss points.
Correct. So we have a loop over Gauss points, and for each Gauss point, what did we compute?
Function value multiplied by corresponding weight of the domain that is applicable to the Gauss. So when you have this 3-node element, you use 2 Gauss points, and then on another domain or on the master domain, the length is obviously 2. So each Gauss point is assigned a weight of 1.
Okay, but you're discussing in 1D, the integration in 1D, right?
Yeah, you said 3-node element, right?
For a 3-node element, yeah. Okay. Yes, now we're discussing integration over triangles. So we do have a loop over Gauss points, but then for each Gauss point, the first thing we did was to compute
as well the functions.
The functions. What functions? The shape functions, right?
Yes.
And the derivatives of the shape functions. So the first thing we do is compute shape functions and derivatives. But those derivatives were given in terms of what coordinates? Global or master coordinates? Master coordinates. And so in order to express those derivatives with respect to global coordinates, we had to compute something else. Who remembers? The Jacobian. So we compute the Jacobian of the transformation, right? And then we use the inverse of the Jacobian to be able to represent those derivatives of the shape function with respect to global coordinates, right? Because the integral that you see here, this is what we're interested in. It's in physical space. We're just applying a transformation here to allow us to compute that in the same way for all elements. So the same thing is here. We're going to be doing the same. So once we have the derivatives of the shape functions with respect to global coordinates, then we can assemble our strain displacement matrix, right? In a standard FEM, we're still talking about standard FEM. And once we have that, we just add the contribution of that Gauss point, which was, who remembers how we did this? So what was the term that we were adding to the 0 local stiffness matrix? So it was B transpose dB times, what am I missing there?
I'm not sure, but yeah, you need the determinant of J.
Yeah, which is the Jacobian, and what else we're missing? The weight. Because this integral that you have here gets actually replaced. So let's write it down. It's a sum over Gauss points, and then we have the B transpose. Of course, this would be corresponding to xi, which is basically the global coordinate corresponding to that Gauss point. D B transpose, and then you have J, and then you have the weight associated to that Gauss point, and that is the way we add the contribution. And indeed, depending on the number of Gauss points, for three Gauss point, guess what is the weight associated with each one of those Gauss points? 1/3, correct. So let's write the algorithm to do this. For one element we're going to be talking about, okay? So for each Gauss point, I denote that psi I. The first thing we do is, indeed, we're going to compute a vector of shape functions and shape function derivatives. In this case, since we're dealing in 2D, this is going to be a matrix. And let's say shapes It's a function shapes that does this job, and then I pass to that function, of course, the Gauss point. So this is compute shape functions derivatives. Yeah. We said also that we are going to compute our Jacobian matrix J, and if you remember, we were computing that by just taking the matrix X, it's a uppercase X, transpose, and then the derivative of the shape functions with respect to psi, which we just got. This was a nice way to compute the Jacobian matrix. And of course, once we have that, we compute the J inverse and the determinant of that matrix J that we call lowercase j, right? So I'm going to put here compute Jacobian, yeah, another things, right? The determinant of the Jacobian is going to be part of the weight. Yeah. Now we compute the derivative of that shape function, of the shape functions with respect to global coordinate x by using the inverse of the Jacobian matrix. And now we are basically ready to at least put all that information into our B matrix, right? So these are for the standard shape functions. So this is basically the part that deals with the partition of unity, or if you remember the formula that had the two terms, where the first part is the standard component, and then the second was the enriched or generalized component. Then so far we can have the part that deals with the standard component put into place. So we can add all those shape functions into our vector container of shape functions, and we can add all those dphi dx into what will be eventually our B matrix. Okay. But now we start to think about the enrichments. So what we do, we have a loop over enrichments, and we're going to call this E alpha I. So E is going to become my symbol for an enrichment function. Well, the first thing we do is we obtain the enrichment, and the derivative of the enrichment with respect to global coordinates. And this can be, let's say we have a function that deals with this computation, and we pass our x coordinate, the global x coordinate. Yeah. So we have not computed the global coordinate. Do you remember how we do this? How do we compute, given a Gauss point, how do we compute the global coordinates that corresponds to that Gauss point?
Inverse mapping?
No. No.
We use the shape function.
Yes, we use the shape functions. And?
The coordinates in the parent element.
Yes, and the coordinates of the parent element. So pretty much what we're doing is interpolating, using the shape functions corresponding to the Gauss point, we're interpolating the coordinate of the parent element to find the global coordinates. So I'm going to say here, well, actually let's move this down a bit. So let's say that we compute our global coordinate as uppercase X, which is a matrix that has the coordinates X and Y coordinates of all the nodes of your element, multiplied by my phi vector. Yeah. So once we have that, we have the enrichments. So these are compute, enrichments, and derivatives. But of course, we are not interested in the enrichments. We're interested in what? What is what we add to the array of functions?
The enrichment functions, right?
Not only. Yeah, so if we go back, what is this function?
Generalized enrichment function.
Yes, that is a generalized enrichment function. How do you compute that?
You multiply each of the shape functions with the enrichment.
Correct. That is the answer. So we're actually interested in computing the generalized enrichment function. Let's call that alpha I, and that is just obtained by phi alpha multiplied by E alpha I. And that is what we're going to add to our container of functions. Okay. So let's write it here, compute generalized, it's called GFEM enrichment function. Yeah. And now we need to obtain the derivatives of those, because the derivatives are the ones that are going to be added to our B matrix. Okay. So, well, the derivative of that function with respect to x, and now we are applying the change rule. The same thing we did above applies here. So we have the derivative of phi alpha with respect to x, E alpha I plus phi alpha, the derivative of E alpha I with respect to x, and the same for y. And then I'm going to put here compute GFEM enrichment function derivatives. Okay. Yeah. And those are the ones that we're going to add to our B matrix. So if you take a look at this algorithm, that is very simple. We have two key points here. When dealing with the enrichment part, we have this term here that is computing the generalized enrichment function, and this is going to be added at the back of our container that contains the shape functions of the parent element, which is the partition of unity shape functions. Okay, and then we have this part that is doing exactly the same for the B matrix, and that is pretty much everything we need to change in our standard finite element package. Yeah, so once we are done with this, we can say, well, let's set phi alpha I and the derivative of phi alpha I with respect to x into phi and b. Yeah, I mean, for this particular case, I'm actually interested in the stiffness matrix, right? So basically, I want to do this computation that you see there. So I only need the B matrix. I don't need to have the vector of shape plus enrichment functions. But of course, the moment you go to do, let's say, body force, and you have to also integrate something that looks like that, you also have to assemble this vector, taking into account the enrichments. So that's pretty much what you have to do to transform your standard FEM into a generalized FEM code when dealing with functions that are smooth inside the element. So if you're applying, let's say, enrichment functions that are polynomial enrichment functions, then you have now with this code everything in place. There is only one thing missing here, is that, well, once we're done with those quantities, then we need to evaluate the contribution to the stiffness matrix. So let's say after that loop here, my contribution to the K matrix plus equal, or let's make it more pseudocode, is KE plus, well, B transposed D B J, which is the determinant of the Jacobian matrix, and W, which is the weight that is associated with that Gauss point, and that's it. We have our stiffness matrix. Okay? Yeah. Now, there was another case. So we said that there are two cases. One was case A, the integrand is C infinity, and another one that is not smooth, right? So let's take a look at what happens when the integrand is not smooth. So we're going to look at case B, and let's picture a problem. Let's say we have a triangle in physical space that is being cut with a discontinuity. We already looked the previous class to enrichment functions for weak discontinuities. So if you think about an enrichment function that can be used to tackle this problem, right? We said that we had to add something about the solution to the problem, some knowledge about the solution to the problem by means of enrichment functions, right? And we look at different enrichment functions last class to tackle this type of discontinuity. So who remembers what enrichment functions we looked at? Yeah, not the heavy side. The heavy side was it's an enrichment function that is used in fracture mechanics, because the heavy side function can reproduce a strong discontinuity. Here we were dealing with weak discontinuities, which were a discontinuity in the gradient of the field. So do you remember what type of functions we looked at?
So function of Mousse or something?
Yeah, the function proposed by Nicolas Mousse. We look at the function proposed by Nathan Sukumar, and these two functions are using the signed distance function in a way. So if you look at these two functions, they basically have a jump in the gradient along the discontinuity. That means that the function is no longer smooth, right? So what we usually do in GFEM or XFEM is we basically subdivide that element in what we called integration elements. So suddenly my triangular domain becomes 3 triangles for this case. Yeah? And there are actually different ways to do that. This is the simplest way to subdivide that triangle in 3 integration elements. Some people take the quadrilateral part of that domain and they determine the centroid, and then they basically create a lot of integration elements around that centroid. But that's more work. You don't really have to do that. Okay, and now we have 3 integration elements. So let's say these are our Gauss points. Yeah, and now something remarkable happens, because suddenly the integration of all those smaller subdomains, right, is performed on a function that is smooth. So our original function was C0 continuous. But by creating these different elements, the functions inside those integration elements are C infinity again. So those are smooth functions. You follow me here? Yeah? So in a way, we have to modify the algorithm that we just wrote to basically perform an integration that is a sum of the integrations of those three integration elements. Okay? So let's write our matrix. So my KE now is going to be the sum. Let's call it S equals 1 to 3. So I have three integration elements, and then I am interested in performing the integration of on omega S. So for example, this one is going to be omega S, and then it's the same thing. Yeah, and now I have sum S equals 1 to 3, and then of course I want to use the same ideas that we have explored using the mapping and so on. So I'm transforming that integral into some isoparametric mapping, right, where I have some Jacobian let's call that JS, which is the Jacobian of that integration element, and some yeah, this remains the same as before. And because we're interested in performing this integration by using discrete evaluations at Gauss points, then that whole thing transforms into something that looks like this. Let's call Q equals 1 to the number of Gauss points, and then we are going to be evaluating this B transpose at those points. So let's call this X. How do we do this? XQ at S, D B at XQ of that corresponding to that integration element, and then we have the Jacobian, and then we have the weight of that Gauss point, and that would be the way we compute the stiffness matrix for that cut element. So now our original integration basically becomes two loops. Before we have one loop over Gauss points because the function that we were integrating was smooth. Now we have a function that is no longer smooth, but by subdividing the integration elements, we make the function at each side of the discontinuity smooth. Yeah? So let's see what are the changes to the algorithm, and then we take a break. So before we go there, I want to talk a little bit about this. So let me ask you, you see that there are, now integration becomes much more complicated than before, because on the one hand, we are integrating over subdomains. So this Jacobian that we have here corresponds to what triangle?
It has subscript S, so it has 3 different values.
Yeah, so that Jacobian is the Jacobian of the integration element. Yeah, but there is something very important, is that the check functions that we're integrating are actually the functions that are belonging to this element, to the main triangular element. Right? Are you following me? That basically means that for an integration point like like this one, right? Somehow I need to do something to figure out what would be the parent coordinate in the original triangle, because that is the psi eta values that I need to compute the shape functions of the parent element. So that is the only trick here. The only difficulty is, well, you're performing integration at the smaller triangular element, right? But once you find out what is the x coordinate, the global physical coordinate for that integration point, you have to do an invert mapping of the second, let's call this the second mapping, right? Which is basically mapping the parent element to your original triangle. Because when you have that psi eta value, then you can compute the shape functions of your partition of unity. Everybody with me here, right? The partition of unity shape functions are again defined in this element, not in this element. Okay, so that is the only thing that changes. So let's make that happen in the algorithm. So what we have to do, well, we have as before, let me see. For each, and I'm going to call this psi I belonging to that integration element in our master element. So basically, if I take this as my integration element, well, I also have a mapping that takes me from that parent element to this element. So this is Q of psi I S. Yeah? Well, at that integration point, I do as before, I compute my shape function vector S. The derivative of the shape function vector with respect to master coordinate, of course, I am dealing with the integration element. Yeah, and we do this by calling the same function as we had before, shapes, and then we're passing that integration point. Yeah. As before, we obtained the Jacobian of the transformation, so we have our J matrix, let's call it JS, which is determined by making my XS. Now these are the coordinates of the integration element transposed into the derivative of the shape function with respect to psi coordinate, that this is S and this is S. I forgot to put S here. So far everything is dealing with the integration element coordinate and the integration element transformation so far. And from here we compute the inverse of the Jacobian matrix, which I call JS. So let me put the superscript S, and this is the inverse. And the Jacobian of that matrix, which is the determinant of that JS matrix. So now what? What do we do? Now that we have the shape functions associated to that Gauss points in the integration elements, what do we do?
You map it to the original element?
Yes, we map it to the original element, but before that I need to compute my global coordinate. Yeah, and for that we do exactly the same thing as before. So we're using the shape functions of a integration element to interpolate the coordinate. So that is going to be my x s transpose into my phi matrix that I call phi s, and then I have my global coordinate. Okay, and once I have my global coordinate, what do we do to find the master coordinate in the parent element, in the original triangular element? So now I have, this is the keystone of the whole algorithm. We have to find that psi I, and notice I'm not using S anymore, so I'm going to put P to represent the parent. And that is basically used by using the inverse mapping Q while passing that coordinate. So for a triangular element, this mapping is actually exact, right? You can get an exact equation that can be used to invert that coordinate. For a quadrangular element, is not the case anymore because of the bilinear term. So in a way, for quadrangular elements, this is more difficult because then you have to solve a nonlinear problem to find the master coordinate. Okay. And then once we have that, once we have the master coordinate of the parent element, what do we do? Now that we have this, what do we do? We are in a position to compute what?
You simply do A matrix, B matrix.
But for that, I need to compute something.
The derivative of shape function.
Yes, and the shape functions, right? So right now, I have really now the master coordinate in the parent element. So now I can compute the shape functions of the parent element and the derivatives of those shape functions with respect to the master coordinate of the parent element. And we do the same by calling shapes. Notice that because my integration elements here are triangular elements and my parent element is also a triangular element, this function shapes is the same here, but that does not have to be the case. So there are some cases where, for example, your background discretization, your partition of unity is composed by quadrangular elements, and then you are subdividing in integration elements, right? So then these functions are going to be different, okay? But I'm passing shapes. Of course, I need the master element coordinate that I just computed from the parent. Yeah, and everything else follows as before. Yeah, so that is the only difference with respect to what we saw. Yes, sorry, you had a question.
It's the Jacobian also should have a subscript, right? Or superscript?
Definitely, this is the Jacobian of the child element, or the we call them integration elements, right? Or children element. Question?
I have a question. How
Yeah.
is that return mapping exactly done? Because you don't. How is it done?
So the inverse mapping.
Yeah, from the sub triangle to
Yeah.
the parent.
Yeah. Okay, so let's take a very simple case, the 1D problem. Cannot get simpler than the 1D problem. So if you remember, our mapping goes basically in our isoparametric formulation. X is a function of the shape functions of the parent element. So you can write X as a function of psi, right? Now what you want is the inverse mapping, right? You want psi as a function of X. Well, it's just a very simple inversion for the 1D. You can make it very quickly, but if I remember correctly, it was psi as a function of X is 2x minus xi minus xj divided by the length of the element, which is x, xj minus xi. Now, it's there is a one-to-one mapping here, right? So the inverse mapping is very straightforward. For a triangular element, this is also the case, right? There is a one-to-one correspondence. But what I'm saying, you have to be a bit careful with the quadrangular elements, because it's very easy to go from the parent element, the -1 to 1 1 square, to your physical quadrangular element. It's straightforward. It's just the same thing we do in all isoparametric formulations. So x is equal to the sum of the shape functions multiplied by the x coordinate, right? But to go from the physical space to the parent element is trickier because of the xy term that you have, right? There is a bilinear term in that expression. Then in order to get to the master coordinate, you have to solve a nonlinear problem, unless of course the geometry the geometry in physical coordinates is basically a square, so there is no bilinear term there. You understand what I'm saying?
Yeah, but it's more. The question is more like, because I get what you're saying. But,
Yeah.
This inverse, in case when you make, because I also have a question about how you subdivide. How do you let the program know how to subdivide the original triangle in 3 triangles?
That you have to do yourself. So that is where okay, we have not talked about that,
Okay.
but in all of these generalized finite element methods for tackling discontinuity problems, there is no free lunch. So something you have to do to figure out what are the elements that are cut by the discontinuities, and you have to do some operations to cut those elements and to create disintegration elements. So that is something that we're going to discuss later on
Okay, so
in more detail.
Okay, so you're going to talk about how to deal with a scenario in which you have pre-knowledge about how the cut goes through the mesh.
Yeah.
And then how to deal with that in the program when it comes
Yeah.
to on the element level, how to subdivide it.
Yeah, exactly. So let me give you a sneak peek of what I mean. Say you have a problem and your discontinuity is a circle, something like that. And well, let's say now that is my element, and I know that I have to do something fancy in that element because the enrichment function that I'm going to be using there is going to be C0 continuous. So say it's just a material interface, right? So what people normally do is they work with level sets. So level sets are basically the distance from a node to the discontinuity. So if I compute the level set of this function, is basically the sign distance that we talked about last class. If we compute the sign distance of that first node here, then the sign distance is going to be negative. Okay?
What do you mean by sign?
The sign distance. The distance from that point to the circle is going to be negative. Now, if I do the same here and here, I'm going to get positive, right? So one way to detect if a triangle is cut or not is you go through the sides of the triangle, and if you detect that there is a change in the signed distance function or the level set function, then you know that there is a cut there. So you can determine with a very simple formula, you can determine these locations. And once you have those locations, you can just very simply triangulate that into integration elements that later on you're going to use to perform integration.
But you also make a straight line between the two crosses, right? Because
yeah, it's a straight line. So in a way, your circle, there is a discretization error in the circle.
The boundary.
Exactly.
Right.
Yeah, but that is the way you do it, and it's very straightforward. In fact,
or I mean, sorry, you mean I mean you're discretizing the discontinuity, right?
Yeah. So the discontinuity is no longer in the finite element solution is no longer going to be a circle anymore. It's going to be piecewise linear, right? Depending on the enrichment functions that you use as well. So what I'm doing here is very simple. Before I start doing all of these enrichments and stuff, of course you need to detect the elements that are cut. So you compute for every node in your mesh, you compute the level set function, which is the distance to a circle, and then you just iterate over the elements to find out where you have a mismatch in this sign, and then you know that that edge is being cut, right? If you know the edge that is cut, then you have the location, you determine the cut location, and you use those to create these integration elements. And of course, the original parent element, you're not assemble that anymore because you are going to use these algorithms that we described in this class to do the proper assembly, right? Because these algorithms, remember, that do not only consider the enriched or generalized portion of the formula, but also the standard part, right? So that is the way you do the assembly. And in fact, this is the problem number 2 in your project. So what I ask you to do in the project is basically to solve what is called the Eshelby inclusion problem, which is a problem that looks like this. Yeah, so the idea that because of the circle, these nodes are going to receive enrichment functions that are going to reproduce that C0 continuity because of the material interface. So you're going to be able to solve this problem in a mesh-independent manner. Yeah, but we extended a lot, so let's make a break here, okay? And then we continue, or we talk about all the things that you may wonder.